All right, great. Well, let me, while people are coming in, maybe I'll just give a little bit of background about me before I jump into the talk. Most of my career I've been an entrepreneur, been involved in open source projects. I left the PhD program at MIT to start a company, Seabridge, that was focused on internet for B2B. Did a bunch of work with aspect-oriented programming, ended up as VP of engineering at a startup, QuantCast, where I really started working with big data and machine learning last decade. Started a company, Think Big Analytics, doing big data and machine learning. We grew that company to about 100 people. We were acquired by Teradata, led that as a business unit in Teradata. Spent a fair bit of time actually here in Copenhagen. We had a thriving team here of a few dozen people working with some of the customers here in the Nordics. So it was, have some fond memories of spending time with the team here. And then, a couple years ago, I left to join Google in the CTO office, really because I felt that AI, the kind of innovations that we were experiencing, led by Google around deep learning that were changing what could be done with machine learning technologies were pretty exciting. And I felt like there was a great opportunity to be a part of having an influence in a positive way on the way AI was landing in the world. In my presentation today, I'm going to talk a lot about what does it mean to be responsible in the use of AI. I'll try to get into a little bit more of some of the technical details around that. But it's still, of course, a survey. There's a lot of deep technical topics associated, and honestly, there's a lot of active research in thinking about this. If you, like me, saw last night's keynote talking about dystopias, I guess I'm a little more optimistic than that, but I do think that a lot of the trends, a lot of the things that we're seeing in the world are things that we have to address, right? We have to think about how technology is landing and what it's doing. And machine learning technologies are a tremendous amplifier for that, both for good and ill, right? So responsibility is actually quite important. So with that in mind, I'm going to give a little bit of an overview. I'm going to talk a little bit about some of how AI is changing things and some of the promise, because I think like all technology that's powerful, it can be used for really good things as well as problematic things, and we should bear that in mind. Then I'm going to talk about some of the problems, some of the kinds of things where it goes wrong. Talk a little bit about some of the approaches we're following at Google and seeing elsewhere around how to be responsible, how to have the right kind of governance, the right kind of techniques. A little bit of a deep dive case study. Talk a little bit more about a concrete example of another company inside Alphabet, a sibling company called Jigsaw, and a case of addressing some problems in machine learning, and then conclusions. So with that in mind, the promise of AI, let's start with that. So in just the last decade, we've seen all kinds of interesting examples of how deep neural networks can learn interesting functions, right? So from pixels, you can come up with labels for what class of object do I see in the picture. And you can hear audio and do a good job of transcribing it into text. And you can do translations from one language to another. And you can do more complicated things like labeling a more complex picture, right? All of these are things that we've really gotten working quite well just in this decade that were, in the realm of someday we might be able to do this, but now these might even seem routine, right? So we've made a lot of progress in the kinds of capabilities that deep networks have. Just to drill in on the vision area, the start of this decade, Imagenet, popular computer vision contest that was really taking millions of images from across the internet and saying, like, how well can a computer do at recognizing what's in a picture? These aren't all simple tasks, right? Like there's multiple breeds of dogs. So people make about a 5% error rate in classifying what object am I seeing in a picture. The start of this decade, 2011, the last year that the winning entry for this contest did not use deep learning, computers were making a 26% error rate. Right, and these were using classical techniques like, here's a bunch of features I can take out of the picture. I can try to see differences in color and try to find lines, and a bunch of manual features with some shallow learning was typically used to achieve this. But within 5 years, the advances in deep learning had suddenly produced this kind of result, rapid improvement to actual superhuman capability, right? Not on all vision tasks, but on this specific task of classifying the objects in a picture, it was achieving better rate of success than people have. And more recently, we continue to see significant application of this technology at Google and in industry. So for example, we just published in our blog the use of deep learning for language understanding and how it's been the top improvement to Google search in the past 5 years. This is one of the examples in the blog post showing how we're now better able to understand the intent of a user when they're typing something in, right? So in this query, the person wants to see how to get a visa. So rather than getting a general article that talks about what's happening with visas, you get a very specific recommendation of what's a place I can go to actually get the thing I'm looking for, right? So that's an example. And this kind of use of deep learning to understand queries is important in search because, for Google, we see about 1 out of every 6 searches that people do is unique. It's never been asked of us before, and therefore probably never asked of anyone ever before, right? So being able to take apart and understand the intention of those kinds of unusual queries is really important to drive better search results, right? So these kinds of improvements, they result in value in how we handle search. Another area in medicine, we've been doing work on diabetic retinopathy. It turns out that this is a source of cause of blindness, that hundreds of thousands of people go blind each year because of this illness. And typically it's because in third world countries like India, it's a long time to travel to a clinic to get tested. And so people don't incur that expensive a journey not knowing that they're at risk of blindness. So it's interesting that we're able to use the same kind of vision techniques, but now instead of recognizing cats and dogs, you're recognizing eye scans, typically just from a phone, and actually achieving a superior result to ophthalmologists, trained medical professionals, right? And this has been gone through clinical trials in India and is being rolled out, right, as a way of giving people a screening tool to identify, hey, you should go get this taken care of. You're at risk of blindness from diabetic retinopathy, right? So an example of a significant benefit. And indeed, we're applying AI and machine learning to a broad range of applications using these new techniques. Google Assistant, new experiences, the ability to talk to a phone or a smart speaker is something that really, until, again, this decade, the experience was so bad it wasn't useful, right? So it's creating a lot of value for people in their homes. And even areas like Waymo, so self-driving cars, where 1 million people a year die from auto accidents. So creating safer drivers has a significant benefit, potential social benefit with autonomous vehicles, right? So there's going to be some real significant benefits from AI, and it's having a big impact for us, and indeed for our customers, right? So in Google Cloud, we work with customers across different industries, and we're seeing a lot of applications of machine learning in a range of domains, including intelligent contact center applications, including improving ability to do forecasting of supply chains, including fraud and risk detection, right? So there's a broad range of applications. But with that in mind, there's also it's a powerful technology, and it can have some real negative impacts when not used effectively, right? And some of these problems include things like bias, having insufficient controls in the system, how it can have impact on society, and longer term negative impacts on users, right? So let's unpack a few examples of these. So a couple of different kinds of bias. One is disproportionate performance. So something works better for some classes of users than others. Others, representational harm, something that a model ends up coming up with a way of representing somebody that is offensive or damaging to them. As an example of disproportionate performance, this is a commercial model, Compass, which is used in a number of jurisdictions in America for predicting if a criminal is likely to reoffend, recidivism. So in this case, you see an example where a white man is deemed by the system to be low risk, even though to our quick inspection it looks like he's got a pretty serious prior records, and indeed he went on to commit another serious offense. Conversely, of a black woman with relatively minor offenses, the system viewed as high risk, even though she did not go on to commit another offense. And these examples are in fact representative of a problem in the system, that we see a disproportionate number of black subjects were labeled high risk and therefore likely to be denied parole, but did not reoffend, whereas conversely, a significant number of white subjects were labeled low risk, but did reoffend, right? So you can see disproportionate performance here on what's clearly a high-stakes decision, whether someone's allowed to get out of prison on parole or is forced to serve out a term, right? So that's disturbing, right, when you get that kind of racial bias in an important decision like that. There are similar examples around financial lending decisions where people from blacks and Latin Americans are experiencing higher interest rates on mortgages than other racial groups. Another example, lack of controls. Who remembers the Microsoft Twitter bot Tay? All right, a lot of you, that's great. It had a short run. I'm sure Microsoft would rather forget about it. But basically, it was put out on Twitter with the idea, hey, it'll just learn by talking to people. And back in 2016, that might have seemed like a more reasonable idea, that there won't be bad actors out on the internet and that you can just put something out there and good things will happen. Of course, very quickly, people taught it to be really offensive and racist, right? And it got taken down. So bad enough that I was told you can't put up the actual tweets to remind people of the kind of stuff it said, but you can find the articles if you don't remember, right? So the basic issue there was building a system where it could be trained by crowdsourced input and not having controls around, well, what's going on here. It became a mouthpiece for really bad sentiments, real problems, right? More broadly, the role of machine learning on some significant societal challenges is important to unpack, right? So I think when you think about things like filter bubbles and misinformation, manipulation of voters, Cambridge Analytica is an example, or just this year, the World Health Organization identified vaccine hesitancy as one of the top 10 global threats to global health, right? Pretty significant, where a variety of factors have come into that, right? In a lot of cases, if you look at how Cambridge Analytica worked, their use of bots, but essentially being able to manipulate recommendation algorithms to get people engaged and to drive sentiment, right? To explicitly create attitudes for voters, for example, to suppress one class of voters and enrage another class to get them to turn out to vote. And similarly, the vaccine hesitancy, promoting fake news that recommendation algorithms were likely to amplify in a variety of media. Again, the consequences of promoting content that was inflammatory was to create a lot of misunderstanding, misinformation, right? So those have had some significant impacts on society, just as examples. Similarly, impacts on users, right? So this article came out just last month in the Wall Street Journal saying, look, Amazon changed its search algorithm instead of to give users what they're looking for, and they're looking for products, to really focus on the products that they want to sell you that are profitable. Now, why is this problematic? Well, I think one is it's deceptive, right? Mostly when you go in to search for something on a site, you expect that the organic results, the results that come up is just, here's what you're looking for, are based on what you asked for, and not based on a hidden agenda of here's what I want to sell you, right? And indeed, in this article, a key thing came out, and I think it's important when we think about responsibility and ethics, right? That that apparently the search division at Amazon got reorganized. So instead of reporting separately up to the CEO, it started to report into the retail division. And then at that point, with the conflict of interest, the retail division started putting them under a lot of pressure to, hey, you need to start driving profitability. We've got a metric on that. Legal, according to the article, said you can't directly optimize for profitability, but all the updates to the search algorithm were assessed based on, are they in fact producing more profitability? So nonetheless, the claim is, look, in the end, it drove to this outcome of worsening the outcome for the user. And indeed, the people in the search division at Amazon, according to this article, were saying this violates a basic tenet of doing the right thing for the user, right? So this kind of, and this one maybe has broader precedence, right? Most of us aren't media companies that are going to worry about how information is circulating in society, but how we treat our users, if we treat them honestly or deceptively, if we create machine learning models that are not transparent about what we're doing, that can have some real consequence, right? And I think this is a kind of fault line that more organizations need to be thinking about. And as we build more and more sophisticated machine learning algorithms that can really influence people's behavior, is how are we doing so in a responsible way? So with that in mind, here's a framework I like to think about in terms of what does responsibility mean. I think at the top level, you have to think about the principles, right? What are the principles you think are important? Every organization needs to embrace their own. I think it's been welcome that there's been a lot of work done on this. Obviously, we at Google published AI principles that I'll share with you in a minute that we adhere to last year, but we've seen that from a number of other large organizations, and indeed, we've seen, for example, here in the European Union, trustworthy AI guidelines in a similar vein, right? So we're seeing more and more effort around what are the kind of principles to adhere to. Then governance, right? How do you really make sure that you follow those principles? And of course, a lot of governance is not new, right? So like in the previous example, avoiding conflicts of interest is a pretty foundational governance guideline, right? Don't put people under pressure to one thing if they're being asked to do something else where there's a conflict, right? And below that, the idea of having different perspectives, both in terms of the backgrounds of the people involved, right? Because especially around bias, but in many areas, different backgrounds give you a broader view, catch more blind spots, but also different backgrounds and professionally, right? So engineers working with domain experts, user experience experts, policy experts can really help. Having more transparency, more ability to understand how machine learning models work is really important for all stakeholders, as I'll talk about, and there's a lot of work on that. And it is important to also have secondary models, so the ways of constraining the way machine learning models work to avoid bad outcomes has a role. But then so does fundamentally, how do you align the objectives of these systems, machine learning systems, with values, with good outcomes, right? How do you think about doing that, right? These are all important aspects of how to achieve responsible outcomes. So, for example, the way the principles we've articulated, there are 7 of them. And starting with being socially beneficial, not create or reinforce unfair biases, being built and tested for safety, right? Makes sense. Accountability to people. You can see how accountability to people requires the ability to be transparent, understand what's going on. Incorporating privacy design principles, right? Obviously, machine learning systems are fundamentally fed by the data we give them, and so privacy is a really important aspect of this as well. Upholding high standards of scientific excellence and being made available for uses that accord with those principles, right? Those are all foundational. And then, on the right are specific kinds of applications that at least Google has decided not to invest in. It's not to make a value judgment on other businesses that might, for example, be weapons contractors, although I think there's a healthy debate about whether we should be having AI-driven weaponry and what the role of AI in weapons is, but I don't want to have that debate in this context. At Google, we've decided that's not an area that we want to participate in. But I think just as important in this discussion is the related topic of what we call our digital well-being values, right? So one of the 3 foundational values of Google is respect the user. And to me, this idea, this growing realization that we need to be more mindful in our use of technology and give users more control over it reflects in these, right? So giving people more awareness of their use of technology, enabling control. And to me, control isn't just about simple simple buttons to say, yes, like turn off auto scroll. Like turning off auto scroll on YouTube is a good thing, but control in terms of what do I as a user want to see and how should this technology work for me, giving me more ability to explicitly influence the way machine learning is interacting with me is a really important aspect of enabling control, right? And delivering benefits without guilt, shame, or regret. And a lot of times, I think a very helpful way of thinking about digital experiences is after use, right? Was it time well spent, or do you regret the use of that, right? And then ensuring user trust. And I think the audience here in the room, everyone who came for this talk shows how much being responsible in AI is important for ensuring the trust of our users, right? So I think this is another aspect that's really interconnected with responsible AI. It's integral to providing digital well-being. And this is just a reminder. I think there's a false narrative out there that I hope you will correct, that people like to say, well, machine learning, AI technology, they're value neutral, right? They're just a technology. But all technologies are used for a purpose, right? And so they achieve the value that's achieved by the people who use them, right? So fundamentally, when we do machine learning, we're choosing the data sources that we're going to use to train on. We're going to and how they're collected, by the way. We're going to determine how the models get evaluated, what's good and bad, and then we're affected by the results, right? So people are intimately connected, and as you've seen in these examples of both good things that can happen from machine learning applied in good context and problems that can happen, they matter, right? So we make the choices, and we should be accountable for them, right? So one of the areas that we start to think about is having, we've put out this idea of kind of nutrition labels, right? Because I think one of the things where people make mistakes is lacking awareness of what data are they using and what models do they have, right? And so this idea of having a data card where you can make sure that people are aware of some key characteristics of the data they're using, including, what are some limitations, right? So it's easy to run into a data set and not have an understanding of where it came from, the scale of it, what are some gaps, and that can be problematic if you're then going to go use it assuming that it's going to work well in a case where it has incomplete coverage or bias or other kinds of challenges, right? So this idea of data cards then is to make it easier for people to be informed in a quick summary about data. Of course, the best practice is if you're going to work on data for machine learning, you should be digging in deeper anyway and really understanding the characteristics of the data. So this is hopefully a reminder to do that, and also a way of understanding more characteristics about the data, right? Like where it came from, the volumes of data, how it's labeled, etc. Similarly, model cards is then a way of documenting and sharing a kind of nutrition label for a trained machine learning model, right? So it will tell you things about like what the purpose is, when it should and shouldn't be used, right? So if you can think of cases where that somebody might be tempted to use a model, but it's not going to work well, it's really helpful to document that, as well as a bunch of statistics about it, like how well it performs overall, maybe performance for certain subgroups, as we'll get into, right? So these are standards we've come up with internally for Google, and I think we're seeing increasing interest in industry around having explicit documentation around the model as well as the data that's used for it as a helpful step to provide more transparency. Now, there's a lot of research that's going into this field of model interpretation. Who's familiar with this area? So not just a handful. So the idea of this is fundamentally saying, if I've trained a machine learning model, I've taken a bunch of input data, and it's going to come back, typically it's for supervised learning, and so classify it, like what is this an image of, or is this person a good, what's the risk this person is going to default on a loan, or, is this, what are sales going to be, the regression of, what are sales going to be next month, that type of thing. Interpreting these models, there's two approaches. One is to try to say, globally, across all inputs, what are the key characteristics that make this model work? What does it look at? How do the inputs to it produce the output? The other is more locally, to say, let me look at the point of a decision, right, and say at this specific point, what are the factors that this model is really incorporating to understand what's going on, right? So there's been a ton of research in the last few years. Several of these techniques have been pioneered at Google, but there's also great research happening in other institutions in academia and other companies. I'm not going to go through all of them. Many of them, however, are what is called a black box technique, which means you can use whatever you want to train the machine learning model, and then I'm going to try to work from the outside and probe it and say, can I figure out how it works without getting into the details of it? Some of these black box techniques require differentiability, so they work well with neural networks where you can differentiate the outcome based on a specific input sample. Others, like Shapley values, do not. They can be used in any technique, even if you don't have that available to you. But others are white box. So, for example, attention mechanisms have become more popular in deep learning. Attention mechanisms basically build a kind of focus across the input to say, what subset of the input am I really going to weigh in my model? So the model builds in a kind of thing that helps you understand what it's doing because it naturally attends to a subset of data that you can look at and say, that's what's driving this, right? So just as an example, a couple examples. Here's a local interpretation. So anchors is research that came out a couple years ago. And it basically tries to come up with a set of rules. I don't know if it's easy to read these, but in this point, here's an age range, a type of work, an education background, et cetera. So it'll come up with a kind of set of decision rules that are highly correlated with the way the model is making decisions, and it can even give you, here's a whole bunch of examples where the rule is holding, and there's no counter examples, right? So this way of understanding how the model's working at a decision point, it's a lot easier to understand this kind of, here's some rules that apply around your case than general. Now, to be clear though, again, this is a proxy model. What does that mean? These rules are just a way of interpreting the way the system works. It's not actually how it works, right? It's a way of translating a complex, for example, neural network into something that's more human understandable. Another example usable in a variety of cases is Shapley values based on game theory concept of saying if you can measure how much a single feature is contributing to a decision by thinking about all the different coalitions, cases where you had it in or out, how important is this variable in deciding the output of the model, right, in a positive or negative way? Right, so it's fairly generally useful. Doing it perfectly is exponentially complex, so typically sampling techniques are used. But again, it gives you a fairly broadly applicable way of identifying what features are being used in the model to predict what's going on. Another one that's kind of interesting came out a couple years ago is this concept of integrated gradients, where the basic idea, the first intuition that you may have encountered is to understand what's going on in a model, you try perturbing the input. Say, like, if we change little bits, how much does that change the output, right? And so the things where if you perturb them, they're changing the output, you have a sense, well, those features are probably more important to the output. However, as we'll see, that's a little simplistic, so this is a more sophisticated technique. In fact, this is being used fairly broadly inside Google for interpreting deep learning models. It's probably state-of-the-art, the most popular technique currently being used. But just to give you a concrete example, right? Here's, like we talked about before with image classification models, here's an image of a fireboat. Now, why did the deep learning network decide that this is a fireboat? So what's interesting is if you look here, these are the gradients. Like at the point of that image, what are the things that if you start manipulating them sort of tell you increase or decrease the likelihood of it being a fireboat? But the point is, in fact, you don't need nearly this much signal to already have the network pretty confident that it's a fireboat. So basically, with just a little bit of visibility into the image, you start turning it up from a black image. Already, you're starting to get pretty confident that this thing is what it is, right? And so the basic idea is, rather than looking at the gradients, where you're way out here where it's flattened out, you already have a lot of confidence once you get to this point where it's flattened out, you integrate over the interesting gradients and say, okay, that means that these lines that really showed the water shooting up are critical factors, right? And so the explanation is a lot better than looking at local gradients by coming up with this summary, right? So obviously there's lots more you can read about this, but just to give it an idea, these are the kind of techniques that are being used to explain these more complicated networks, right? And I think it's valuable. These can be very valuable. The people that probably most benefit, though, from this kind of explanation are actually the engineers who are working on these problems, right? Because in some sense, these explanations are reducing what's a model doing to what are the features that are driving the input to the model. And the reason I mention that is because I think that this can be problematic in some cases, that often end users won't understand, or non-experts in the domain won't understand how to interpret such models. And the other thing that I think is worth cautioning a little bit is, in many cases, these kinds of explanations, you'll see examples done in terms of images, because we all have really powerful intuition about an image, and we can make up a story. But I'll show you an example in a minute of a case where a model came up with an image interpretation that leaves you to realize, I don't know what this model is doing. Right, here's another example, though not on images, of applying integrated gradients. Here's an example looking at a model that's trying to predict what are the factors that cause the police in San Francisco to stop people, right? And you can see that the weekday and the day of the week were big factors. What was this, a violation of a restraining order? Was it in a particularly bad neighborhood of San Francisco, right? The hour of day were all kind of the key variables that the system comes up with among many that were being used to identify what moves the model, right? So it makes a complicated machine learning model based on neural networks much simpler to understand. Now here's the example I was telling you about, right? So those examples, the success examples look great, but on the left you've got a network that calls that dog a cat. And then you've got the explanation up top, right? That heat map is like, well, here's why we think it's a cat. And you're left going, I really don't know what this model is doing. Because when I look at that part of the dog, I don't see a cat, right? So cynically, it's like, these explanations can be really good for explaining things when I already know what it is, and it appeals to my intuition. And sometimes it's more useful, right? There's another example I've seen where it shows a little boy with a red raincoat looking out with binoculars, and it calls him a clog, and you can kind of see in it, okay, I see why it thinks that. And there are other cases where it's been found useful in image models. There have been some medical cases where the explanation has shown, oh, the thing that it's latching onto is the human-written notes on the chart that diagnose it. Okay, that's a good clue to say we need to be careful about our input, right? But again, like, hey, these turned out to be really good diagnostic tools for the engineers, but can be really dangerous in a way for broader use, right? That they're probably not so helpful for non-experts who don't know the meaning of these variables, right? And so I like this paper Professor Cynthia Rudin wrote at Duke recently, pointing out, look, we have to really think about this. Instead of using these complex black box models, interpretability is a really desirable characteristic, and we should strive for models that are more understandable, maybe even at some loss in precision in the models, but also saying in a high-risk case, doing the extra work of really trying to find higher precision models without relying, ones that are black box, where these explanations are at best proxies, right? And it's interesting, her example of that same one I showed you before of the system that's predicting recidivism. where the 130 variables, very complex, some problems. It turned out you could also come up with a much simpler set of like 3 rules that works just as well and doesn't exhibit bias, right? So a great example of maybe you should, so when you're working on this, the higher the stakes, the more valuable it is to think about coming up with simpler models in the first place and really not just latching onto the first thing that works. Another thing that I think is really valuable is using visualization tools, right? So we've put out a number of tools to make it easy to slice and dice data, and you can divide it into subpopulations and different characteristics. And so spending time asking about a machine learning model, how it's working and why it's working and where doesn't it work, where does it fail. Using these kinds of tools, I think the open source community has come a long way, so I'd encourage you to learn about them. Right, here's another example of doing TensorFlow model analysis. Again, being able to look at how did different groups perform, right? Really helpful for bias, but also can be instructive for other purposes too, right? So there's some good tools out there available for creating better understanding. And then, just as important, I think, is you should have multiple metrics of what's going on, right? And what are the overall effects of your system, right? So a lot of times too, when you introduce changes to a machine learning system, there can be feedback loops. It can take time. A lot of changes that we make in systems initially roll out. They may not have much of an impact, but if you give it some time, you start to see that user behavior will adapt, and you'll see longer-term trends. That can be good, right? So it means you don't necessarily want to give up just because as soon as something rolls out, you don't see behavior change. But it also means you need to watch for longer time, right? And see, are things happening that I didn't expect, right? So classic examples of this is not only can you look at things like what are people clicking on, but where are they spending time? What kind of feedback do they have? How do cohorts are exposed to it? How are they retained? What sentiment are you seeing? This idea of pin day you see is sort of what is the performance of the system for a subgroup of users rather than across the whole, right? And comparing these things as you're running tests, right? A/B tests, or if you're using more sophisticated techniques like multi-arm bandits, right? Basically keeping track of a variety of metrics, and think about what are metrics that would give us some indication of things that might go wrong in the system, as well as ways of measuring the health. Super important, right? So that's an important thing. Where you can, try to simulate these in advance, but the reality is most of the machine learning systems that we build today are fundamentally about correlations, and we're making our best guess about causation. So there's no substitute for running tests carefully designed to really understand what's going on, right? Even if we're optimistic from back testing that something will work. Another area that we've invested in, we think is relevant, is secondary models, right? So doing things like catching policy violations or inaccurate information or toxic comments, sensitive items, right? So in this example, this conspiracy video questioning the moon landing, YouTube will pop up this information box below to link you to an authoritative source saying, here's the Encyclopedia Britannica article about what happened with the Apollo space program, right? So that's a secondary model. On the other hand, I think we've now done a lot more to not amplify and promote conspiracy videos on YouTube, and I think that's probably had a bigger impact, not recommending them in the first place, rather than putting a little disclaimer below them saying, hey, this is probably false, here's the truth, right? Or not probably false, it is false. Let me just be clear. Finally, I think there's a lot of room to really spend more time thinking about what are we optimizing, right? Classically, there's been a tendency to optimize really simple variables like clicks, right? And then over time, we're realizing, wow, we need to have more nuanced ways of what we're optimizing. I think that's going to be more and more of the direction, right? So I think we're going to try to, well thought out systems will do things like try to optimize for time well spent instead of time spent. And yeah, that's more complicated, but working on how do we come up with reasonable proxies to optimize in these circumstances is worth the effort, rather than sort of optimizing simple things and then trying to constrain the damage that ensues when there's unintended consequences. I do think this is an important area, right? And there's long-term research in the AI community around value alignment, which is a really hard problem, saying, can I somehow infer what people's values are from their behavior? That's going to take some time, right? But in the meantime, I think as engineers, we can do a lot more and should do a lot more to think about what might go wrong by optimizing this, and how do I change and refine my loss function in my machine learning system so that I'm really optimizing for something that's going to produce good output, combined with those secondary metrics. And there's a case study around fairness. So Jigsaw is a sibling company to Google and Alphabet, and its mission, it creates open source software to help create, in this case, perspective to help with moderation of online communities, right? So to identify toxic comments, attacks on people, hate speech, etc., right? Now, unfortunately, because certain groups of people are subject, certain minorities are subject to a lot of offensive language or used as a slur, the first version of the model that tried to identify toxic language learned that bias, right? So you take these two statements, I am straight and I am gay. It thought the first one was not toxic, slight toxicity, and the latter one it thought was quite toxic because it had seen that language used in a variety of slurs, right? Obviously, this is a representational harm and bias, right? Not good to identify that statement as a toxic one. And so one thing is to say, well, can you think about how does the prediction change if you change the identity token, right? And you can see that it varies, that some groups are viewed as more toxic than others by this first model, right? Depending on how often they're being used in a negative context. And you can also do a variety of metrics to identify errors, right? How effective is this system at identifying correctly toxic language when you've labeled it? And you can see certain groups are perform extremely badly, right? As you can see, especially LGBT. But in thinking about that, there's been a lot of work in the last few years on ways to create better models that can be more accurate and that we can actually drive the models to do better on different groups. So there were a few steps we had to take in order to improve on this, right? One was to actually take certain characteristics and say, well, what if we generalize, right? So instead of training on individual identities, come up with a way of mapping those identities to a generalized token, and so the model can no longer discriminate among identities and say we should have the same behavior for any kind of identity. Another one was to actively collect more data, right? The system had skewed data, and so we did a project to go out and crowdsource and collect more positive statements about some of these groups where the model was underperforming, to balance it out, to have more examples, right? Because fundamentally, if you have biased training data, you're going to have a hard time producing an unbiased model as output, right? So actively collecting good data was an important aspect to this. And then finally, changing the loss function, right? So making it so having performance on different subgroups be important and not sort of just aggregate performance was important too, right? Because fundamentally, if you have a minority group can get very bad performance in a model, and the model might, if you were just assessing the overall model performance, it might say, hey, this model's performing well, right? So if you want to, you can constrain it and say, no, we want to do better in training for all these groups. And that will tend to be a trade-off of slightly worsening overall performance, but in return for more fairness, right? There's no free lunch, but an important characteristic, right? And so the net effect was that these effects, when the sixth iteration of the model, dramatically reduced this kind of bias, right? You can see that the pinned area under the curve is much closer across these different groups. And if you're wondering, it's like even with that, there still can be leakage and characteristics where there can be complex interactions where it's not a simple problem to solve, as you can imagine. But by applying these kinds of techniques, you can do a lot better at coming up with an unbiased model. So, right, the lessons were to test early and often, right, to develop multiple metrics and measure the scale of the problem, and take steps in your modeling to explicitly address it. So just to conclude, I think a few things I'd say is, one is to take responsibility, to be explicit and think about the broader implications and risks. As an engineer, that to me means always thinking about the bigger implications of your work and what might go wrong, and feeling free to ask the questions. Second is to broaden participation. Say, how do we get user experience people involved? How do we get people who have maybe policy expertise involved? How do we get, how do we make it? And often as an engineer, you can be the bridge into the third one of transparency, which is right now, there aren't great tools for communicating in understandable terms to non-engineers. But if you understand it, you can help be that bridge and help them understand it. And so I think transparency to let all stakeholders have an understanding is really important, and it's a role that we as engineers can play to really tell that story and create the right visualizations and help people understand what's going on. Right? And then finally, driving value alignment, really thinking about the right metrics and the ways to what to optimize for, as well as constraints. If nothing else, I hope you take away that when you're working with machine learning systems, you really want to think about the metrics and objectives and how to optimize them for what's responsible. And these are some different things. We've published People in AI Guidebook, about integrating AI into user-centric design and responsible AI practices you can look at. Also, I think worth looking at the EU's ethics guidelines for trustworthy AI. And with that, I just have a few minutes here at the end for any questions you might have.